handout that I gave last time, the 3-6, and I do have a couple more 3-6s up here if anybody wasn't here last time, but I am posting all these things on D2L. So what we're going to look at is the idea of displacement, velocity, and acceleration. Okay, so the idea is typically in physics we use the letter S to represent please do what you're supposed to do. There we go. Okay. All right. So we usually use the letter S to represent displacement. That just means how far you are on a trip from the beginning. Okay. So typically, like in a straight line in one-dimensional motion, we might say like S is 0. That's the beginning of the journey. Okay. That's where you start. And as you're moving away from that starting point, displacement, we say basically this. It's just the difference between these two things. These can be thought of as a function. So you're taking the function f of a plus delta t. Now that delta t, what that's representing is that's really representing a change in time. Okay, so maybe 2 seconds from now, you've moved from this point to this point, like that. Okay, so that's what we mean by a displacement function, is it's just your position at a particular amount of time, which can be represented by some type of a function then typically, okay? If we're looking at the calculus of this now, so we're going to find that what I'm trying to show you on this graph that I've got in black here is a position function. So this is S equals f of t. And what this is saying is this might be your starting point right here. This is where S is equal to 0 right there, and then you're moving away from that point. So basically, you're moving away as the time changes. So your time axis is going like this, and then your position is going like this. So you basically have a t-axis, and you have an s-axis, like that, okay? And what you're doing on this then is the velocity is going to be like a tangent line, so it's going to be given a rate of change. So we can think of the instantaneous velocity as a rate of change of the position over a period of time. So this is trying to represent the tangent lines, and you would notice on this thing that the velocity would change because the slope of that tangent line would be different. So right here, it's a pretty steep tangent line. And then as you get way past here, then the tangent line kind of levels off to a point where it's almost at a slope of 0. So that's what we mean by an instantaneous velocity. And the secant lines give average velocities. Now, we've already talked about that earlier in the semester. Now we're ready to formalize this now that we know how to do derivatives. And that would be kind of the idea. Okay, so as I move down on this, this, again, would be the average velocity. And the average velocity, again, just think of that as a secant line like we learned. And if you have a secant line, what are you doing? Okay, it's like a slope formula. You guys know the slope formula from your background is y2 minus y1 over x2 minus x1. That's what you learned in an algebra class. So that's really what this is doing. This is giving you your change in your y values. And then that delta t is really given the change in those x values like this. So this is the way that you write this a lot in physics. You use that delta symbol to represent that it's a change in some quantity like that. Then the instantaneous velocity, well, that's going to be now a derivative. That's a slope of a tangent line. So hopefully you guys see that this is the definition of a derivative. You're taking the limit as this goes to 0. You're used to seeing h in the difference quotient, but you can still think of that as delta t. And then again, that's really just taking your secant line and taking the limit as t goes to 0, okay? So one of the things I said, earlier when we were talking about this is if you have a function, you can think of a tangent line as 2 points on a curve that are infinitesimally close to each other. That's the idea. So you're taking this limit, you're basically just taking these points so that they're very, very close to each other. That's the idea, okay? So this at this stage is nothing new. What's going to be new about this is since we know how to do derivatives now, then we can formalize this a little bit better and be able to do derivatives to find velocity and acceleration and so forth, okay? All right, so I'm going to move to the next page, and then we're going to do an example. It'll kind of give us an idea of how this works. So I took this one basically out of the book. This is a pretty good example. This is supposed to be representing an airplane. So what I've done is I've graphed S of t. S of t is this function. It's not defined mathematically, but it's just graphically. So this is supposed to be like a plane, and its displacement over amount of time. So right here at time equals 0, at time equals 0, well, you're just at the airport, right? Okay, you're at the terminal. You haven't taken off yet. You're getting ready to take off yet. Okay, but then what's happening is this is your position miles from Seattle, from the airport. So you're getting further and further. Like, for instance, after 1 hour, it looks like you're about 300 or so miles from the airport. And then as you get like to 2 hours away, then you're basically around 12 or 13 or 1,400 miles from the airport. Okay? Then what happens is all of a sudden it just levels off. Now what would that mean? This piece right here means basically that your position's not changing. So what happened? If the airplane's position's not changing, it doesn't just stop in midair. What happened? It landed, so it's back at the airport. Okay? So at this stage right here, you're at the airport wherever you were going. Now what's happening is you're basically just returning back to where you started, like this. So now you're back in flight, and what's happening now is you're going towards that initial place, like that. Now one of the things that happens on this is the velocity. Of course, an airplane starts with a very small velocity, so if you look at the tangent line right there, you know, that's a velocity, but it's getting bigger. So typically what an airplane does is its velocity increases, then it hits maybe 500 miles per hour or whatever, and it stays that way roughly through the journey. Then, of course, what does it do? It starts slowing down to prepare for landing. So you have some pretty steep velocities there, and then when you get to that point when you're ready for landing, then it just starts basically leveling off again. Does that make sense? Okay. And then what happens is velocity, if you're going back to the returning point, what kind of tangent line slopes do you have now? You have negative slopes, right? And you can have a negative velocity. All that means is your direction is changing, okay? It doesn't mean that you're slowing down. It just means your direction's traveling. So what's happening is you're going from the airport, you have positive velocities. Then when you're returning back to the original place, then you have negative velocities. So velocity can be positive and it can be negative. And that you don't want to confuse that with speed. Like the speed of a car is always positive. But velocity is directional, so it can be positive or it can be negative. All right, so does that graph and that scenario kind of make sense to everybody? Yeah, okay, that's a pretty good example. So you can graph out your displacement if you're traveling in some way, okay? All right, so we're going to answer just a couple of questions about this. The first thing on part A is we want to calculate the average velocity for the first 1.5 hours of the trip. Now we're going to estimate on this basically, so what I'm going to do is we're just going to find two good points, okay? We're supposed to be going from 0, so 0 is that point, and then 1.5 would be, I'm going to say it's probably that point right there, so we need to just get those 2 points. So we'd have a point 0, 0. What that would be representing, of course, that would be the beginning of the journey, and then this would be the displacement at 0. So you're at the airport. You haven't taken off yet. This point right here looks like it's about 1.5, and I think that's probably probably 600. Let's just use 600. So what that means is this means that the displacement after 1.5 hours, what's the 600 mean? It means you're 600 miles from the airport. So that's what that means. So if you're going to find the average velocity, just think of it like a slope of a secant line. So we're going to do this. We're going to do S of A plus delta t, which is this. So we're going to take that minus this. So we're going to take 600 minus 0. Just think of this as finding a slope. Then you're going to do delta t. Delta t just means what's the change in time? So that would be 1.5 minus 0 like that. So that's going to be 600 over 1.5. And then you could take your calculator and crunch that out, and then you would have what your average velocity is like that. Okay? All right, now, and don't confuse this with instantaneous velocity. What this is doing an average over a time interval. So if we do 600 divided by 1.5, that looks like that's going to be about 400 miles per hour, like that. Okay, does that make sense to everybody? Okay, now we're not doing an instantaneous velocity yet. We're just doing average velocities like that. Okay. The second part of this problem said that we want to do a average velocity from 7.5 to 8.5 hours. Okay, so what I'm going to do on this is we're going to get a couple of points on this. So let's look at 7.5 appears to be right in here. So I'm just going to estimate what that point is. Okay, it looks to me like at 7.5 hours, that would appear to be let's see, that's probably let's say 300. Does that look okay? All right, I'm just estimating. Okay, and then we're going to look at, I think they wanted you to look at 8.5. So 8.5, that would appear to be at the point, what looks like to be 8.5 and 0 right there. So what's happened at 8.5? You've landed, right? Okay, so we're going to find the average velocity on that. And if you do that, let me just ask you a question. Do you think that average velocity is going to be negative or positive? It's going to be negative because you're going back. Remember, velocity is directional. So we're just going to do this. We're going to do 0 minus 300 over 8.5 minus 7.5. Just think of a average velocity as finding a slope of a secant line. So it's negative 300 over 1. So that would be negative 300 miles per hour. Okay, and it's okay for velocity to be negative, but if we were talking about the speed, and I'll talk about the speed a little bit later, like if we said the speed is always defined to be the absolute value of velocity. So that's like what you're more used to seeing, like when you drive your car, the speedometer is always reading a positive value because it's technically not directional. Speed's not directional, like that. Okay, so that's how you would crunch out average velocities. Does that make sense to everybody? Okay, that's a pretty good example to show you how you can graph a displacement and tie it to some scenario. So let's see, this part C, it says at what time is the velocity 0, okay? So if you look at this graph, when would the velocity be 0?
3 to 5 hours?
Yeah, it looks like in this area here, okay, so that would be one interval. Of course, obviously, it would also be 0 at the beginning of the journey, so it kind of looks like somewhere in that interval right there, your velocity would be 0. Because it's a slope of a tangent line, so it looks like the velocity would be probably on that interval, probably 3 to 5. That would be my guess, best educated guess on that then, okay? All right, so we would say the velocity is 0 from 3 hours until looks like 5 hours. And what's the plane doing at that point in time? Okay, it's like refueling or whatever. Okay, it's landed. Okay, it's at the airport. Okay, I guess it's at the airport is what I'm supposed to say on that then. Okay, so that's the idea. Okay. All right, now let's look at what happens on just kind of estimating. We're going to estimate what the velocity at 6 is. Okay, so if we wanted to find the velocity, now we're looking at an instantaneous velocity right here. So we're not looking at a slope of a secant line. So we're going to do this by estimation primarily. So let's go to where 6 is on this, and we're going to draw like a tangent line on this. I'll try to do a tangent line on this, or at least I'll try with this to kind of make it at least fairly accurate here. And you can just sort of draw a tangent line, all this. All I want to do on this is just have us kind of estimate that. So this would be your velocity at 6. Now, first of all, does that look like it would be negative or positive for the slope? Negative. It'd be negative, so it's sloping downward. So what we want to do is just see if we can pick a couple of points on that tangent line, and that would be one way to estimate it, because all we're doing is estimating on this. So we're going to definitely use that point right there, which is, that looks like a point, what do you think, 1200, like that. And now take another point on this. Now again, we're just estimating on this, so I'm just going to say maybe at, gosh, I don't know, 7, let's say at 7. Now you're on the tangent line, you're not on the curve. Let's say at 7, maybe you're at, say 700. Okay, I'm just taking a rough guess on this. Okay, you guys see what I'm doing on that? Is I'm just looking at this tangent line right here, and I'm trying to take 2 good points on that tangent line. And this is obviously an estimation problem. So when we do this now, we could just go through and then we could find the slope of this. We could go 700 minus 1200 over 7 minus 6. So that looks like that's going to give negative 500 over 1. So that looks like that's about negative 500 miles per hour, like that. Now that was an estimation. And that's pretty reasonable for a plane. Planes usually, that's a pretty typical speed, okay? So let's see. This one, what it's saying is the velocity is really negative as the plane is returning to the original point. So this is just kind of the plane's turning around and going back to the original airport's what it is, okay? All right, so is there any questions about anything I did with that problem? Okay, a lot of that stuff is we've done a little bit before, but we haven't really looked at displacement yet. That's what's a little bit different about that. Okay, let's move on to the next page here. And we're going to do now, I'm going to look at, the formal calculus definition of this. And you guys, if you're going to take physics, I guess a lot of you are going to take physics someday, you'll deal with this in Physics 1 all the time. So velocity is really what it is it's just the derivative of the displacement, okay? And then speed is the absolute value of the velocity. So one thing that I said a few minutes ago is the speed is always positive. That's a pretty good thing to write down. And then velocity is directional, so velocity can be positive or it can be negative like we had on the last example, okay? And here's kind of an example that I want to just show you on these graphs here that'll kind of help you with this a little bit, I think. So let's say, for instance, that you have this position. This is a position function, and this is given by t squared minus 5t. So the velocity would be the derivative of this, which you can do in your head now. That's 2t minus 5, which is a line. So that's the position, that's the velocity, okay? And that's the graph of the derivative. So one thing I want you guys to notice on this is, let me ask you a couple of simple questions on this. What do you think the velocity would be at this point right here? Because it's a slope of a tangent line. What is the tangent line at that point? Okay, it's level. So notice that you have 0 right there, okay? The value of the velocity has a function value of 0 there, okay? If you look at this part right here, do you have a negative velocity or a positive velocity in this region right here? It's negative, right? You have negative sloping tangent lines. So one of the ideas is in this region right here, what are you going to have? You're going to have negative velocities, okay? And then notice that in my graph of the derivative, don't I have negative y values? Okay, that's the idea. Okay, the other thing is, what kind of velocities do you have in this place that I just highlighted? You have positive. So look at your graph of your derivative. You have positive y values. Now, of course, we've learned about the graph of the derivative, so you want to make sense of this as you're understanding these concepts. Now, what the acceleration is acceleration is a rate of change. So it's a rate of how your velocities change. So imagine you're in your car. If you press the accelerator, doesn't that change your velocity? Absolutely. Okay, if you hit the brakes, that changes your velocity also. So acceleration is how your velocity is changing. So it's a second rate of change. So it's defined to be the second derivative, okay? So when you do an acceleration, it should be the derivative of the velocity. So notice on this, if you do the derivative of 2t minus 5, you get 2. And if you graph 2, that's a horizontal line like that, so it's a constant acceleration like that. So basically what would be happening on this graph of this position, you would have a constant acceleration, okay, like that, okay? All right, so that's what we mean is if you want to find the velocity, you do the first derivative. If you want to find the acceleration, you do the second derivative, okay? So that's one application of the second derivative then. Okay, now let's do this second example here and look at this. Now with this one, what we're going to do is this one you're given a position like this. Now if you take physics, you'll learn about specific projectile motion equations, which are quadratic equations. So they're basically saying that you have a height of 192, and then it says you have an initial velocity of 64, and then, let's see, I think that's all that says on there, and then you have an acceleration due to gravity is 12 feet per second squared. That acceleration due to gravity is different on different planets and different places, asteroids and whatever. It's because of the mass is what causes the gravity to change. Like, for instance, on Jupiter, very massive, very high gravity. The moon, not as massive, has less gravity, like that. So basically, you'll learn about this projectile motion equation in physics. So what we're going to do is, first of all, we're going to find the velocity. So if you find the velocity, what do? You do the first derivative of the position function. Now you're to a point where you can start doing these derivatives in your head, hopefully. So this is going to be negative 12t plus 64, okay? Now notice on this, you'll learn about this in physics, is the formula right here is when we did that derivative, we ended up getting that acceleration due to gravity by doing that, okay? And then when we do the acceleration is going to be the derivative of this, which is going to be negative 12, okay, like that. Okay, so now what we're going to do is figure out when the stone reaches its highest point. Now, without going through the details, I'll graph this on the graphing calculator in a minute, but this is a quadratic function, and it's going to be going upside down like that, right? That's what's going to be happening on the problem when we graph this, and you're going to have a height of 192, like that, okay? So when does the stone reach its highest point? Well, what we do is, what's special about this highest point right here is the velocity. What is the value of the velocity at that high point? It's 0. Okay, so if you want to figure out when the stone reaches its highest point, what you do is you just take the velocity, which is negative 12t plus 64, and what do you do with it? You set it equal to 0. Okay, and that'll give that to you. So now you can solve this equation. So you could move the 12t to the other side, so you would get 64 equals 12t. Then you can divide by 12, and then this would give you the time when this occurs then, okay? And I want to leave my calculator up here as I'm doing this, and then we'll do a graph here on this in just a minute here. Okay, so let's go ahead and just get a decimal answer. So 64 divided by 12 is going to give about, let's just round that and say about 5.3 seconds is when that happens. Okay, so that's how you can find the high point, is by looking at where the velocity is 0. Okay, all right, and just kind of answering this, this says the highest point is reached at an instant when the stone changes from moving upwards, and that's going to be a point where the velocity is positive, okay, and then it's going to be moving downward. That's going to be a place where the velocity is negative, so it must occur when the velocity is 0, like that, okay? Now I'm going to go ahead, if you want to do this on your calculator, if you got your calculator, get that out, because I'd like to show you a couple of things on a graphing calculator with this that are kind of nice to show students at this level. So I'm going to put in y equals, we're going to put in this position function, we'll use x's instead of t's, of course. So we're going to say -6 t to the second, or use x to the second, plus 64 times x, and plus 192. Now you obviously have to set up your window on this to get a good picture of this. But one clue on this is the high point's 192. So your y-axis needs to go at least up to 192. So here's what I'm going to have you do on this. I'm going to start on the window. X is 0. Time is 0. We're not going to ever use negative time. And then let's take this up maybe. Notice the high point. It reached the high point at 5.3 seconds. Just take an educated guess. It doesn't matter. Let's say 15 and then maybe scale that by 5. And then for the y's, let's go. I actually am going to use some negative y values on this. There's a reason for this. Let's go down to -50 and let's go up to 200. I'm using 200 because the high point's 192, and then maybe scale that by 50. So you want to put that in and then go ahead and do a graph, and then you'll see a position function that will be a quadratic function like this then, okay? All right, so let's see. It looks like I may need to make that go up. You know, actually, the 192 was the original height on that. Let me get that fixed here. So I've got that okay. Probably need to make that go up a tad bit. Let's maybe make that go to 500. Up. And maybe make that y minimum go to -100. Let me just try that and kind of get that adjusted. And then maybe try the scale like that, because we want to see a whole picture of what that function is. What I wasn't considering is 192 is not the high point it ever reaches. That's just the initial position like that. All right, so there's you a better picture of how that projectile goes like that, okay? Now, if you want to see something really cool, you know how I am about this stuff, try this. I think almost all calculators do this. You can take your cursor and you can get it blinking on that line, and you can press enter, and it'll change this. I just like to show this because I think it's so cool. Okay, you can change it to a ball. Okay, now if you press graph, look what happens. Ooh, isn't that cool? You can see the projectile of the ball. Okay, like that. All right. So I think most all calculators will do that. You also have like there's the ball and chain, which is what I like to use a lot, because that way it sort of shows the motion of it. So you can go like this if you want to. You can kind of scroll and experiment through this stuff. That one right there is called a ball and chain. So if you graph that, it'll show the ball, but it'll also trace out the motion like that. Okay, you got to admit that's pretty cool. Okay, now what I'm going to show you on here is just a couple of things that are kind of nice to be able to do on this problem. Like, for instance, we just found the maximum height was 5.3. Well, try this. Type trace and then put in 5.3 and put in a couple of decimals like that. And see, now it's blinking on the high point, so you can use that to verify that that's correct. Okay, so your calculator can actually do this, but the calculus is what we're learning, so that's how you can find that maximum value like that then. Okay, right, now what we're going to do on part C is what is the height of the stone at its highest point. I just did that on the calculator by putting in 5.33. That 362.66 comes out. So what we're going to do on this, though, is we're going to go ahead and write the position function, and we're just going to evaluate that at 5.33. And let's use 2 decimals so we get a little bit greater accuracy on that. So we're going to go up to this position function, and we're just going to work out -6 times 5.33 to the second plus 64 times 5.33 plus 192. And if you work out the details on that, you're going to get about 362.7 feet. I've already kind of done that on the calculator anyway. Okay. All right. So we used calculus to find the amount of time that it took to reach the maximum value, then plug that into the position function to get what that height is. Okay. All right. Now the next thing we're going to do is on this is we're going to look at when does the stone strike the ground. Okay. Well, if you look at the graph here, this is where when it hits the ground. So what is the value of S when you're on the ground? 0. Okay, so that's the whole key. So the stone strikes the ground when S of t is equal to 0. Okay, like that. So that would be, I don't know what I'm meaning by the 4 thing. The key thing is S of t is equal to 0. Okay. Right, so that's what we're going to look at, and it would end up, what we would do is we'll just take we're going to do this mathematically. We're not going to do it with the calculator yet, but I'm going to show you how to do that. So what you want to do is just write down the position function, which is negative 6t to the second plus 64t plus 192, and we're going to set that equal to 0. And we're going to solve that equation without a calculator, so this is now really an algebra problem. It's not a calculus problem. So one thing I would probably do on this, you can either factor this or potentially go the quadratic formula, but one thing I'm going to do is I'm going to divide everything by -6 and probably go the quadratic formula is what we'll end up doing on this. So let's just divide everything by -6. And that'll simplify the quadratic formula a little bit. So we're going to have t squared. Then if I go through and do 64 divided by 6, let's see, that's going to be 2 negatives. So that's going to be, that's going to be minus 10.67. Let's round that like that. And then if we do 192, and divide that by 6, let's see, that's 32. I'm just going to use decimals because all I want to do is get an approximation on this anyway. And that needs to have a t in it, so that's minus 32 equals 0. Okay? Then we'll go through and just solve that using the quadratic formula. Okay? And you can do it this way if you want to. You can use a decimal. So let's put this in the quadratic formula and then get this solved. We'll find the value of t when it reaches the ground. So the quadratic formula, you have negative b, like s, then you have plus or minus square root of b squared. So that's negative 10.67 squared. That's your b value, minus 4ac. So a is 1. C is negative 32. And that's going to be all over 2 times a, so it's like that. I assume you guys remember the quadratic formula, right?
Yeah.
If you forget it, you can always look it up, okay? You have heard of such a thing, right?
Oh, yeah.
Very good.
Totally forgot.
Okay, now let's just do this kind of in one step. Now we're not going to go through, we're just going to kind of work out that radical in one step. So you can do this. You just go square root and then just put in, and that negative is going to become positive anyway, so I'm just going to go 10.67 squared minus 4ac. I'm going to put in the negative 32, and see, this way I'm going to just go ahead and do the square root of that and then just record that. So I'm going to record that as about 15.55, then all over 2, like that. Now, in this problem, the minus makes no sense because you would end up getting a negative value for t. So what you're going to do is just 10.67 plus 15.55 over 2 and just work that on your calculator down. So 10.67 plus 15.55, get that answer, and then divide that by 2. So it looks like around 13.11 seconds is where this happens, okay? So that looks like that's where you're going to reach the ground, and then we'll look at the graphing calculator. I'll show you kind of how to check this and verify this, because one of the things you want to be able to do with technology is use it to verify. So what I'm going to do now is you can type on your calculator, you can go back to your graph and press graph, and if you do trace 13.11, okay, you can pretty well tell that's pretty close to where you reach the ground because it's the cursor's blinking on that point. Okay, it's off a little bit because we rounded. That's the only reason. Okay. Okay. So does that make sense? If I want to find when something reaches the ground, what do? You set the displacement equal to 0 and solve the equation. All right, that's the idea. Okay. Okay, now let's do one other thing with this thing. If I press the wrong thing on here, it always screws up. Okay, so let me move this over.
What is the quadratic formula again, though? Is it a plus or minus?
Negative b plus or minus square root of b squared minus 4ac all over 2a. There's even a song on YouTube that you can learn to sing if you would like.
I would definitely.
Okay, and you can come to class next time and sing it for us if you'd like.
It's all goofy. That's how you remember it, you know.
Okay. All right. Okay, so let's do one more part of this then. Come on, stop this. I quit using my mouse. The mouse always messes the thing up.
Is that your Kachina doll there?
What's that?
Is that a Kachina doll?
Yes. It's going to come in handy for what I'm going to teach today in the second section here. Now, where is everything? Where did all this stuff go? Okay, so on the next thing here, there's one other part of this problem I want to do. With what velocity does the stone strike the ground? So what you're going to do on this is you're going to take the velocity function, and we found that 13.11 seconds is when that happens. So if you want to see what the velocity is when it reaches the ground, that's what you're going to do. So the velocity, remember, was negative 12t plus 64. So what you're going to do is you're just going to work this out and then calculate that out. Now it's going to be a negative velocity because of the direction it's going. So we're going to do negative 12 times 13.11 plus 64, and then that will give a velocity of about negative 93.32 miles per hour. Okay, and it's negative because it's going down as it strikes the ground. It's going in a negative direction like that. Okay, so that's a pretty good problem to start us off with on just looking at the calculus of velocity and acceleration. Okay, any questions about anything on that? Okay, so how do you find the velocity? Derivative of position. How do you find acceleration? Derivative of velocity. Okay, most of the questions we're asking on that are going to be calculus applications, either finding the maximum height or when it reaches its maximum height and so forth like that. Okay, so if you do take physics, you will learn a couple of things. I don't have you guys memorize these formulas or anything, but for instance, if you're looking at projectiles on this, basically these are what we call the different projectile motion equations. So that's the way that is. S naught is like your initial height. So on that last problem, that was 192. There was the velocity, the initial velocity. G is the acceleration due to gravity. So that is basically a quadratic function for projectile motion. On the moon, this is your equation. They're like that. And then your derivative is your velocity. Your second derivative is your acceleration, like that. Okay? So basically, there's a couple of things on this, like the Earth's gravitation, you guys may or may not know, is negative 9.8 meters per second squared. Okay? And then on the moon, the acceleration due to gravity is negative 1.62 meters per second squared. So that ratio is about like this. So you end up with a ratio that you can formulate by that. So I just threw that in because that is something that we can do, is use those projectile motion equations. Okay, so a couple of questions on here. Then I want to move on and finish this up, and then we're going to do one other basic type of application. So just a couple things I took out of the book. If the derivative is large, then small changes in x are always going to result in relatively large changes in y, okay, because it's a slope. So if you have a real tiny value of x, what's going to make that slope large is a large value of y changing like that, okay? So what's the difference between velocity and speed? Okay, I said velocity can be positive or negative, right? And speed is always positive. So basically the speed of an object, you want to write this down, is the absolute value, and just abbreviate that, is the absolute value of its velocity. Okay, so the velocity encompasses the direction that the object is moving while the speed does not. Okay, that's the idea. So you're going to, if you're asked for speed, you're doing an absolute value of a velocity. Okay, velocity is directional. Okay, a couple other things I wanted to talk a little bit about this. This says you have an object that's moving along a line, and it has constant negative acceleration. Okay, so the idea with this would be is we're going to look at a couple of things on this. If you had constant negative acceleration, what that would mean is if you were to graph out if the acceleration was a negative number, and if it was constant, I'm just going to give you an example. Let's just say, for instance, the acceleration was -3 meters per second squared. Acceleration, the units are like meters per second squared, feet per second squared, like that. You would have something like this. Okay, that would be, if you had constant acceleration, that's the way the graph of that would look like. Okay, and if it was negative, it would be something kind of like that. So if the object is moving in the positive direction, then you want to think about what the velocity would be. Well, the velocity, remember, the acceleration is the derivative of the velocity. So you would have to kind of reason this out like this. The velocity, if you're going to do a derivative of a line, of a linear function, and if that slope was always like -3, I'm just going to give you a real specific example on this. Like, for instance, if you had a velocity like this, let's say, for instance, you had the velocity is, let's say, -3t plus 3, okay? -3 is, notice I have a rise over a run, -3 over 1, like that, okay? So if you had a negative acceleration that was constant, that would mean the velocity would have to be a line sloping downward. It's the only thing that's possible. So notice in this, if this is the velocity, then the derivative is the acceleration, so that's -3. So if the object is moving in the positive direction, okay, well, that velocity is always going to be negative, isn't it? So it's always going to be negative in this case, and if the velocity is moving in the negative direction, then it's still going to be negative. So the idea with this is going to be your velocity is a rate of change that's going to be negative, so that's what you would end up getting if you had a negative acceleration. Okay, let's do one additional thing with this before I go on to the business application here. And we're just going to do a couple of derivatives and do one more thing with this. Okay, so let's take a look at this particular problem. So we're going to be given this function, and it's going to be defined from 0 to 5 seconds like this, and we're going to find a couple things. First of all, let's do a graph, and let's do this on the calculator and put this in. So typically this is going to be a projectile represented by a quadratic function. Okay, so let's clear off what we had and put this in. A little bit simpler value on here. So we're going to say -x squared plus 4x minus 3, like that. And let's see, we're going to, for a window, we're going to do this. We're going to go 0 to 5, because that's what I said to do, is 0 to 5. Okay, and scale it probably by 1. And the -3 is going to be a y-intercept on this. So let's do like -5. And let's do maybe, let's just start by saying maybe to 10. And maybe scaling that by 5. I'm just going to start it that way. We just want to see a picture of the quadratic function from 0 to 5. If I have to adjust it, I'll adjust it. Okay? All right, so that's a pretty good picture. I think I'll change this a little bit. Let's actually go -5 to 5, and let's go by a scale of 1. So put that window in. You can put that on your calculator if you want to. And then we'll graph that. So I'm going to have you just make a real kind of rough graph on this thing then. Okay, so let's, on part A, just draw a graph. Label this T for time in seconds. Then we're going to go out to 5 seconds like that. And then we're going to go up to 5. This is going to be S of t, like this. Okay, that's going to be your displacement. And then let's go down to -5 like that. Okay, and we're just going to get a couple of points on this basically. So it looks like from the graphing calculator seems to show that possibly you have a intercept at 1 and 3. So let's put an intercept on there and just get a rough graph. Put an intercept there, put an intercept there. You also have a y-intercept at -3, and then just kind of sketch it like that, and that's good enough. Okay, so we're going to do a couple of things on this as we're doing this. Okay, you should be able to do this in your head now, hopefully. So what would be the velocity of this function in your head? -2t plus 4, okay? What would be the acceleration? Since it's the second derivative, what's that going to be? -2. So this would be an example of a function that has a constant acceleration. Okay, like that. So it's real easy to use calculus to find velocity and acceleration, and typically your position functions are going to be polynomials, okay? Now what we're going to do on part C, we're going to determine the velocity and acceleration of the object at t equals 1. So this is real simple. We just do v of 1, and then we're going to do a of 1. Okay, so if the velocity is -2t plus 4, so we're just going to replace the t with 1 and then work out the arithmetic. So -2 plus 4 is going to be 2. So that would mean the velocity at 1 second is positive. Okay, now look at your graph. Look at this graph up here. Here's where t is 1, right here. Does it look like that's a positive velocity there? Yeah, there's a positive tangent line there. Okay. All right, now let's do the acceleration at 1. What do you think that is? It's -2. We already figured it out. The acceleration's never going to change. There's no variable in that expression. It's just -2. This thing has a constant acceleration to it. Okay? Then in part D, we're going to determine the acceleration of the object when its velocity is 0. So if we want to, first thing we want to do is we want to figure out when the velocity is 0. Okay, using calculus. It almost looks like it's going to be at 2 seconds based on a graph, because it looks like your tangent line is going to be horizontal at 2, but let's find out specifically. So you want to take your velocity, -2t plus 4 equals 0, and you want to solve that equation. So that's 4 equals 2t, divide by 2, so you're going to get t equals 2, okay, like that. So the idea is determine the acceleration when the velocity is 0. Well, at t equals 2 seconds, the velocity is 0. But what is the acceleration always on this problem? -2. Okay, so you didn't really even have to do that. The acceleration is guaranteed to be equal to -2. It's constant on that problem, like that. Okay, so that's kind of some of the things that you'll be doing on these problems, is just working with position functions, velocity, acceleration. Any questions there? Does that look good? Okay, the derivatives are going to be easy on this stuff, so that's not going to be the big deal. Okay, so let's just kind of wrap this part of this section up here with, I want to give you guys a little time to see if you can figure out this problem right here. Now, I've given you a position, so what I want you to do is find the average velocity of the first 45 minutes of the trip. find the average velocity on this interval, and then find the average velocity on this interval, and just kind of describe what you think the motion would be from 9 a.m. to 12 p.m. And the way this works out on this is this basically says at this original point right here, that's going to be when we start timing, that's 9 a.m. And this is a position, and it's given its location t miles after that. So this would be like 1 hour, 2 hours, 3 hours, and so forth like that. Then what I'd like you to do is go ahead and work with that problem number 2 just a little bit, and then we'll take a break. So go ahead and I'll give you about 5 minutes to work on those problems, and we'll take a break. Second half of class, we're going to do one other application of this. Then we're going to start into what we call the chain rule in the next section here today too. Okay, so part A, okay, tell me if you got the point 00.7530. Does that look good? Okay. All right, so then basically all you're going to do on your average velocity is you're just going to do 30 minus 0 over 0.75 minus 0. So that's 30 over 0.75. And crunch that on the calculator, and then you'll have your solution on that then. Okay, so let's see, what is that? 30 divided by 0.75, what do we get here? About 40, does that sound good? Okay, 40 miles per hour. Okay, part B, let's see, 0.2510, I got that. And how about 0.7530? Is that the points that you got? Sometimes I have a real hard time seeing on these little graphs here, so I think that looks good. Okay, we're going from 0.25 to 0.75. Okay, so the average velocity on this is going to be 30 minus 10 over 0.75 minus 0.25. So that's going to be 20 over 0.5. So that looks like 40 also, if you do that. Okay, is that what we're getting? Okay. And then the next one, 1.75, I ended up getting, I came up with 15. And then 2.25, that looked like about negative 15 to me. So the average velocity on that would be negative 15 minus 15 over 2.25 minus 1.75. So that's negative 30 over, what's that, 0.5. So how about negative 60? Does that look good? Okay. All right. Now, what you're really doing on this next problem is you just kind of describe the motion of the patrol car. So basically what's happening is, you know, if I was describing this, I would say from 9 a.m. to, and let's see, this would be like right around 10 a.m., a little bit past 10 a.m. We'll just say around 10 a.m. Okay, so basically it's moving from the station, right? So it's moving to some destination. It's going from the station. Okay, now what's happening then is it's changing its direction. So what it's doing now is probably from, and I'm estimating, from about 10 a.m. to about 11 a.m. Well, it's going back to the station. Okay, so it's going back to the station. All right, so that's what it's doing. It's going away from it, then it's going back. So it goes back to its point like this. Now, what it's doing now is it's moving from the station now, but it's moving in an opposite direction. So you might say, okay, maybe it's moving north. I mean, directionally it doesn't matter. So maybe it's moving north and then south. Now maybe it's going to south from the station to some other place. So it looks like from about 11 a.m. To about, let's see, that's maybe about, I'm just going to estimate and say like about 11:30, not being too specific there. Then it's going maybe southward, that doesn't matter, but it's going southward from the station, and then at 11:30 on, then it's just heading back towards the station. So that's the idea, is it's moving away, then back then it's moving away to a different place that's in a different direction, and then eventually it's heading back like that. So that's kind of the idea. Okay, does that make sense, what I'm talking about with the average velocity and just an interpretation on that? Okay. All right, well, let's do this last one here, and then we'll take a break here. Okay, so the graph on this is a cubic function, basically. And if we put in the cubic function, and I have this cubic function in. So I just wanted to sketch on this, and you can kind of do that. So basically we got negative 6t to the third plus 36t squared, and then minus 54t. Now my window on this, I did this like this. Of course, you're going from 0 to 4 because that's what the problem specified. And I went negative 25 to 25. That was a pretty good window to get the whole graph put in there. And then you would have something kind of roughly like this. So I'm just going to sketch this out. So let's see, you're going to go 1, 2, 3, 4. That's the t-axis. And then the function kind of looks like it's going to be down close to negative 25. And I'm just going to roughly sketch this in. I'm not all that interested in something that's 100% accurate, but just the idea like that. Okay, so what we're going to do on this is that's the position function. Now we're going to find and graph the velocity function. So first of all, the velocity you should have got negative 18t to the second plus 72t minus 54. Okay, because that's the derivative of the position function that we get there. Now what we're going to do is just graph that, and it says when is the object stationary, when is it moving to the right, when is it moving to the left. Okay, so if you look, for instance, at this graph right here, the only time when it's going to be stationary, it's really what it's doing is it's moving kind of like in a south direction. Then basically it changes directions. It looks like at 1 second. Okay, then it goes back to its original destination, and then for that instant in time, it's changing directions like that. So when is the object stationary? Okay, first of all, it's going to be stationary. That just means it's not moving, and that's only for an instant in time. That's going to be at x equals 1, or actually not x equals, we should say time equals 1, and we should say time equals 3. Okay. Now, the way you would solve that with calculus is what you would say is you would say, take the velocity function and set that equal to 0. That would give you this minimum and this maximum. Those would be places where it's temporarily stopped because it's going to change directions. Now, you can actually take this and solve this by hand. You could divide both sides of that quadratic function by negative 18. And that would give t squared minus 4t plus 3 equals 0. That could be factored, and that factors as t minus 3, t minus 1. So that gives you t equals 3, and that gives you t equals 1. So that problem right there can be done without a calculator. It can be done with calculus, so you can identify those stationary points then. All right, so when is it moving to the right? When is it moving to the left? Well, the idea on this basically is I'm going to go ahead and graph the velocity here, because you're also supposed to graph the velocity. So the velocity function is quadratic. So that's negative 18 t to the second plus 72t, and then minus 54. And I'm going to do that in probably a similar window, although I'm probably going to need to adjust that. So we kind of have the velocity going like this. So basically it's going to be moving to the right. You can think about this. The velocity is positive in this direction right here. So until it gets to that point right there, and I may have messed my window up there a little bit. So it looks like until you get to this point, the velocity is going to the right since the velocity is positive. And that's going to be moving to the left because the velocity is negative like that. So what you would say on this is it's basically going to be moving to the right On the interval, it looks like from 0 to 2, and then it's going to be moving to the left from 2 to 4 like that. Now, if you look at the original idea on this, basically what's happening on this is this velocity is really always going to be increasing from that point to that point like that. So when you put the graph in, let me make sure I got the graph in there okay. The graph of the derivative would show you positive velocities in here and negative velocities in there like that, okay? Now let me correct something on this. I just saw something that I didn't do right, and I was looking at that graph the wrong way. So where is the velocity positive on this? It's from where to where? This is where you're positive, from 1 second to 3 seconds. So that means that you'd be moving to the right from 1 to 3. I wasn't paying attention. I did that wrong. So from 1 to 3 seconds, you're going to have positive velocities, okay? Then you have negative velocities from 0 to 1, and then again from 3 to 4 like that. So that would be kind of the idea, is you're moving to the right when the velocity is positive, which would be in here, and then you're moving to the left whenever your velocities are negative. You can also look at the tangent line on this. So if you look at, if I highlight this graph right here, the only place where you have a positive tangent line is from 1 to 3, right? Okay, so that's where the velocity is positive, and then these two regions where you have negative sloping tangent lines would be when you're moving to the left. So that's how you figure that out, okay? Okay, any questions about that? Okay, well, let's take a 10-minute break here, and then when we come back, we've got just a few things to finish.